Okay. So, Moritz. Thank you very much for the introduction. Today we already heard a lot about different talks about how we can make FPGAs and hardware synthesis more accessible to software programmers. And one topic that I want to talk about today that we've also heard several approaches about is code generation for high-level synthesis. You also heard this, we have an ever-increasing need for computational complexity in all sorts of areas that you might think about. We have architectures that can deliver this performance, mostly specialized architectures. So we have a multitude of different options that we can use to solve our problems. And most likely, any of these might be suitable for the specific domain that we want to target. So for software programmers, we have well-known architectures, GPUs, we have normal CPUs, and now into the market come new embedded architectures, such as SoCs from Xilinx and Altera, FPGAs from different vendors, but also, for example, embedded GPUs. We've included embedded GPUs since they almost target the same area as an FPGA. You might also use them for terms of power efficiency. So we also heard something about this today or in the morning sessions. What is the state of the art to solve a problem efficiently on one of these specialized architectures? You need to have a thorough understanding of how the target architecture works, and most likely you have to adhere to some specific coding techniques to make use of this architecture. Most likely this will result in an efficient solution, but you have a highly optimized handcrafted solution, which is typically specific to this architecture and most likely only to this generation of the architecture. Once the vendor comes out with a new generation, your old code might still work, but the performance might not be there anymore. And it's very difficult to port it to a different architecture. Think of a specialized GPU architecture. Try to bring it to the FPGA. If you've written it in CUDA, you might have a problem to transfer it over there, and several things like that. And of course, these specialized architectures are difficult to maintain. Let's say the developer who made the specialized architecture moved away from the company. You have to maintain his specialized code. You have to know all the tricks that were built inside there, so you might have a very hard job for that. So this is the state of the art for software. How is it about FPGAs? In FPGAs, many companies have not yet accepted the high-level synthesis flows. So you have the traditional flow, which you all know. You make a functional design specification, most likely in a high-level language, such as C, C++, MATLAB, anything like that. From there, you test, validate, tune your design behavior until you've arrived at a behavioral model. And from this behavioral model, which describes what is going to be solved by the algorithm or by the solution, you have to come to the architecture, meaning the RTL implementation, which specifies how the problem is specifically solved. And most likely this involves hand coding RTL, which is the most common source of errors for hardware design. Specifically, you will spend most of your time in debugging and testing your code down here in this area. So the problems with this is that the increasing design complexity makes this much harder to manage hand-coded RTL projects. Process geometries keep shrinking, so you have a lot of different effects from the hardware itself, like power, like temperature, like increased frequencies that you have to use, and all those little problems that will cause this. And moreover, this methodology has not changed for over 20 years, so we're trying to use 20-year-old methods to develop current systems which really need high complexity. High-level synthesis has made this a little more convenient. You replace the hand-code RTL step for some things, as we've heard today, with high-level synthesis. You're lucky if you can accept a flow like Altera, when like it was introduced this morning, where you can have your whole FPGA system, you can download it, they make all the interconnects, all the I/O already for you. But most of the time you'll use high-level synthesis to simply make one accelerator into your system. So the benefits are you have an increased productivity, you have simplified specification and verification. Think about C, test benches in C versus test benches in VHDL. However, you have the same problems for the efficient solutions as we've seen just before. You need to be familiar with the FPGA architecture and the coding styles for it. simpler array accesses versus line buffers and windows, for example. And also you have, once again, handcrafted designs, which might work for the current version of the compiler that you're using. If there might be a compiler update, you might run into problems again because stuff doesn't work anymore. So the challenge that we've targeted is how can we have all these problems for mitigated and target different design architectures and achieve portable, efficient solutions. More specific, what do we need? The very popular 3 Ps. We need performance. Performance should be portable, not only for one architecture, but for a multitude of architectures. It should be competitive, meaning it should be comparable. The performance should be comparable to handwritten code. It must be productive. The algorithm should be able to be specified on a high abstraction level, so you need to hide all the low-level details from the actual developer. And it should be portable. It should support different target architectures from one algorithm description, and it should support different target languages from the same algorithm description. And the solution that comes to mind about here are domain-specific languages, which offer both functional and performance portability. In this talk, I'm going to talk about the HiPAC, Heterogeneous Image Processing Acceleration Framework. HiPAC has been around for several years. You can download it freely off the internet. It's under a simplified BSD license. How does it work? You have a C++ embedded DSL. Then you use a source-to-source compiler, mostly using CLang and LLVM. Combined with domain knowledge and architecture knowledge, it can put out CUDA for NVIDIA GPUs. It can put out OpenCL for AMD. You can put out C, C++ for x86. And also we've targeted embedded GPUs. You can put out RenderScript to target embedded GPUs which are in tablets and mobile phones. HiPAC is a framework for image processing, so you are in the image processing domain. So the domain analysis for image processing, of course you have several types of kernels in image processing. You apply point operators, which in which an output pixel is determined by a single input pixel. You apply local operators, where an output pixel is determined by a neighborhood of pixels. And you have global operators, where the pixels of the whole image contribute to the result. Therefrom, you have the following domain-specific instantiations in HiPAC. You have an iteration space, which defines the region of interest of the output image. You have an accessor, which defines the region of interest of the input image. The accessor combines filtering, and we have boundary conditions, of course, in image processing. You need to think about, especially with local operators, what am I going to do at the image boundaries. So we have several boundary handling models, and of course we have a lot of convolutions in image processing, so you have a mask. What does this look like in HiPAC? I have the example of a simple Gaussian blur filter. First of all, you have the image data type, which defines your input and your output. For image, you can have any type. It doesn't have to match between input and output. For example, we get unsigned char in, we put out floating point, and for the image, it's simply a matrix for which you define the width and the height. The next thing is you define a mask. In this case, it's a simple Gaussian blur, so you have a floating point mask. To accelerate this, you can pre-compute the mask to do the convolution. Next, we define a boundary condition. Boundary condition, for example, a clamp, where you just clamp your image boundaries to the outside to be used for local operators. We could also do mirroring or anything else like that. You define an accessor. The accessor, as made before, defines which region of the input image do you want to compute to obtain the output image. And of course, you have the iteration space, defining which pixels of the output do you want to calculate. And this is, of course, the output image. You define your Gaussian blur filter by giving it the iteration domain. You're giving it the accelerator, the masks, and in this case, the convolution window size. We're using a 3x3. The radius is 1. And you call the filter simply by calling the execute method, and then you output your result. How does a kernel look in HiPAC? In HiPAC, we have a class kernel, and we can make a class Gaussian blur, which extends the kernel class. As you can see, a kernel usually has the mask, accessor, and a radius. Usually, you don't need anything else. In this Gaussian blur example, we also take an iteration space into it. And then you simply define your usual kernel, which is a simple two for loop or two nested for loops to define the convolution. What we now propose, we simply extend HiPAC to be able to generate code for high-level synthesis. We're currently using the C++ backend from HiPAC to interface with Vivado HLS. This could also easily be modified to use the OpenCL backend from HiPAC to go to Altera. We could use C to go to Lagap, as we've heard this morning. This would also not be a problem. And together with domain and architecture knowledge, we can generate target code for the FPGA by using the C++ for Vivado HLS and generate HDL for FPGA. HiPAC also gives us a golden reference for the algorithm and for the test bench that we have supplied to it. And what is not depicted here, but since the question came before, HiPAC does not only generate the actual accelerator code, HiPAC also generates a host part. So you will not only get the actual code for the FPGA, but you also get the host part specifying what you have to do on a normal computer where you want to execute the accelerator, for example, on a PCI Express. So how does it perform? In previous work, we've compared HiPAC versus OpenCV. OpenCV is included with Vivado HLS. And we've compared several image processing algorithms. We compared Laplacian operators in size 3 by 3. The D means diagonal, the D means horizontal. The H and the O means H is the HiPAC implementation, O is the OpenCV implementation. And we've also compared for the Harris-Horner detector for a radius of 3 by 3. And you can see here on the left side, it's the hardware resources in percent. We've just depict the 4 usual hardware resources: lookup tables, flip-flops, VRAMs, and DSPs. The results are post, place, and route. And on the right-hand side, you see the maximum frequency that we can route. This here is not a frequency point, that's just the index. And you can see for the Laplacian operator, for example, we can achieve very, very, very efficient implementations, also at very efficient clock frequencies. And for the Harris-Horner implementation, HiPAC, for example, uses more DSPs, meaning it goes into the floating point data path earlier versus the OpenCV implementation, which goes into the floating point data path later, so it performs more fixed point computations, which is why it uses some more flip-flops and some more lookup tables. The other hand side, we've usually you do a line buffer, which is the same height as your window. If you do some tricks, you can reduce this line buffer size, which is also why HiPAC uses some less DRAMs than, for example, the OpenCV implementations. A nice thing about this is we cannot only generate code for the high-level synthesis, but we can take the same code base and generate code for embedded GPUs, for normal processors. And since we are image processing domain, we've taken a server-grade GPU, the Tesla K20, and we've taken a embedded GPU, the Armani, and we've compared the throughput that we can achieve. So here on the left-hand side, we have the algorithms that we've taken a look at, which is the Laplacian operator seen before, the Harris-Horner detector, and we've also made an implementation of the optical flow algorithm. And what you can see is the scale then here is logarithmic. So you can see the Tesla K20 is still miles ahead of the Synth. But one thing that jumps to the eye is that the GPUs decrease in performance with the amount of work that you have to do per iteration. Also, the Tesla decreases with the amount of work that you have to do per iteration. In a Laplacian operator, you don't hardly have to do any work per iteration. But on an optical flow or Harris-Horner, there's a lot of stuff to do per iteration. So the GPUs decrease, whereas the FPGA solution hardly decreases. So, I mean, there's some difference, but mostly what you can see from here for FPGAs, as long as you can cram the logic all into the FPGA, mostly what decides its performance is the number of iterations that you have to do. Except you find a way how to get that number smaller, but that's mostly the way that defines the throughput that you can get on the FPGA. So we thought Harris-Horner and optical flow are already quite challenging, so we're going to put some more resources into the FPGA and expand it to multi-resolution applications. What are multi-resolution applications? Multi-resolution applications analyze designs on several different levels of these resolutions. Typical applications are wavelets, noise filtering, image blending, multi-grid equation solving, and you have this typical structure, meaning you have a pyramid on which the lowest or the base level has the original resolution, and you go into smaller resolutions as you go up. You can make your life easy by simply cutting the resolutions in half in each dimension. So on each following level you only have a quarter of the data. You can also do it by cutting it in three, but then the computations get kind of ugly. So pyramid structures in HiPAC. HiPAC recently introduced pyramid support. You have a data structure that automatically creates and encapsulates multiple images of different solutions. And you also have a traverse method by which you can traverse between the different resolutions, which also encapsulates the functions for the computations. And with that, of course, you can do V cycles for image pyramids, but you can also do W cycles, which are very common for encoding and also for equation solving. We've analyzed two applications. The first one is a Gaussian pyramid for multi-resolution bilateral filtering. We've done this for 512 by 512 images. So on the top level, you have a 512 by 512 bilateral filter, and of course you have the downsampling for the next lower level. The top level, we run this at an iteration interval of 1, meaning in each clock cycle we process a new input pixel. On the next level, we only have 256 by 256. So what we can do, we can either supply its own clock and cut that clock by 4 to make it run in synchronous mode, or in high-level synthesis, much easier, we can just increase the iteration interval by forcing it, for example, to 4, so that these two stages can run completely in sync. And for the next levels, this goes down to actual 6 levels. On the lowest level, you do not have to perform any more downsampling, so we can simply run the bilateral filter and have an iteration interval of 1024. Up here, we need a dedicated operator for each operation. Down here, we can make our use of operator sharing, because we have the larger iteration interval. Now you see the V cycle. First of all, we go down, and then we go up again, because in each and every level, we first do an upsampling, and then we combine the results from down here with the results in the current stage. So all of these are local operators, meaning you get a lot of delay, meaning you have to buffer a lot of data. Remember, this runs with an iteration interval of 1, meaning it reads 1 in every cycle, and after a certain delay, it produces 1 in every cycle. So you have to combine, you have to wait until everything is rippled down through here until you combine here. So you get a lot of delay here, so meaning you have to do a lot of buffering. Same structure is a Jacobi multigrid solver used for differential equation solving. With the Jacobi multigrid solver, you do a smoothing of your current data set, then you restrict it, meaning you do a downsampling, and you pass it on to the next section where you also do a smoothing of your grid, and then you also do a downsampling again, and smoothing, downsampling, until you came to your lowest resolution. You can go down to 1 by 1, meaning for the equation system you only have one variable left. Same thing applies here. You need a dedicated operator for the uppermost level, which runs it into that iteration interval 1, and we can do operator sharing on the lower levels. Also, once again, you have the V cycle, and also you have the very memory-intensive waiting from the solutions from here until all the stuff has been computed from down here. On the way up, you do a prolongation, meaning you do the upsampling of the results from the smoothing, and then you correct your solution with the previous solution on this level, and then you do another upsampling and go up all the way. Experimental results for 512 by 512, no problem to fit the stuff on the FPGA. We can fit a 3 by 3 bilateral filter. We can also fit a 5 by 5 bilateral filter, although the 5 by 5 already has a lot of hardware resources that it crams in. However, it's quite easy on the VRAMs that we need. For the Jacobi solver, we need a lot of VRAMs because you need to do a lot of buffering. So it's quite easy on the hardware resources, but it's very bad on the memories that we need. How does it perform? We've compared it to the ARM Mali, and once again you have the logarithmic scale, and you see all these 3 filters perform about equal on the sync, due to it all being run at the same iteration interval. However, the Mali cramps in significantly as soon as you need to do more. A 5 by 5 bilateral filter is way more challenging than a 3 by 3 bilateral filter. So conclusions. Code generation can deliver truly portable, efficient implementations. It already provided great results for simple image processing, and now we've shown that we are also capable to generate very complex structures. And one cool thing, my colleague Oliver, who is co-authoring this paper, finished the results, or finished the product yesterday evening, and it is now available on GitHub. So if you want to try it out, if you want to try HiPack and the FPGA backend, you can go to GitHub and get it and download it. Okay, thank you for the attention, and I'm open for questions.
We have time for 2 questions.
Yeah.
When you looked at the different implementation architectures, GPU and so on, did you look at the energy use or just the performance?
We looked at the energy use. We have made a very detailed comparison, and we have a publication coming in October at Coders where you can see this in all great detail. We've compared the energy of the GPU of the Tesla K20, the embedded ARM, and the Synth. So you have a very...
What's the answer?
Of course, if you need the performance of the Tesla, the FPGA, well, you have to do partitioning. You have to cut the number of iterations down that you have to compute on the FPGA. So if you can partition it, for example, to 4 FPGAs, or you have a simple filter and can partition that to 4 accelerators, you can get within the vicinity of the performance of the Tesla, and then you're way more energy efficient. And also, the FPGA is way more energy efficient than the embedded GPU. That's the
when you
solution.
say way, is it a factor of 100?
I don't have it in my mind at the moment. You have to look at the other publications. Yeah?
For these comparisons between FPGA and GPU, the GPU presumably uses floating point math, but in the FPGA are using fixed point math, or is it also floating point to the same precision as the GPU?
It is the same code. So if we instruct the GPU to use floating point, we also use floating point on the FPGA.
Okay.
If we instruct the Armani to make use of its vector units, we've created a high-level synthesis design that can synthesize vector units in Vivado HLS.
And it would instantiate Xilinx floating point cores then?
Yeah, of course, as Vivado HLS does.
Right.
Okay, thanks, speaker again. Our next speaker is some